Okay, guys, welcome to Unit 8. Unit 8, we start Chapter 5, which will take quite a while. These sections are loaded with information. So, here we go. Fundamental identities. This is on page 191 of the trig book, but there is so much more than what you see here. However, I am going to go over every single one of them. But basically, my advice, and it has been the same for a while, get some index cards, make some flashcards for all this stuff. If you have these concepts memorized, then it's so much easier to do the work. If you have to keep looking them up, it will completely slow your progress. So, everything in the tan box here is important, and then some. You'll see what I mean in a second. But here's what I'm going to do. I'm going to break these down one by one. The easiest one to understand is the negative angle identities. It's at the bottom of the list here, but since we just got through graphing, it's easy to illustrate this one. So here's basically how it works. If you take the sine of a negative angle, it's equal to negating the sine of that positive angle. And the same thing, what's good for sine is good for cosecant. What's good for tangent is good for cotangent. And you'll notice sine, cosecant, tangent, cotangent all have a similar pattern. The one that is a little different here is cosine and secant. These two guys are a little bit different because if you take the cosine of a negative angle, it doesn't equal negative cosine of that angle. It's the same as if it were a positive. Now, what does that really mean? Well, let's look at the graphs so I can illustrate this for you. So, here we go. Negative angle identities. This is my first Roman numeral here. So here's the concept. I drew myself a sine graph ahead of time so I wouldn't have to do it later. But, excuse me, let's just pick on an angle for theta. So I'm going to plug an angle in here. And what the heck? I'm going to use pi over 2. Okay? So I'm going to say pi over 2. So what does the negative angle identity actually say? It says, well, if I took the sine of negative pi over 2, what would my result be? Well, sine of negative pi over 2, what do I get? Well, that's what I get. I get negative 1. Well, then let's take the sine of regular pi over 2. Well, if I take the sine of regular pi over 2, I would get positive 1. Well, those things are not equal to each other. They would be if I were to put a negative on this. That would mean I'd have to put a negative on this. Then these two dudes would be equivalent to each other, hence the negative angle identity. So if I take the sine of any negative angle, as long as I take the sine of that same angle and put a negative in front of my function, I get a true statement. That's what it's all about. So when you're working through a problem and they give you the sine of, let's say, negative 30 degrees, well, if you would rather, you could just say, you know what, I'm going to use the sine of 30 degrees and just make sure I put a negative in front of my answer. That's what they're talking about when it comes to negative angle identities. Now, let's look at the cosine one because that's the only one that's different. And you can draw a similar situation for any of these negative angle identities. You can. You can draw a I'm going to erase my markings on there. You can draw any of these graphs and do this. But I just figured we'll talk about sine, we'll talk about cosine. So here's the cosine one. What does the cosine negative angle identity say? Well, It says if you take the cosine of a negative theta, negative whatever angle it is, it's the same as the cosine of the positive version of that same angle. So for example, let's do one that's real easy to see. If I let theta be pi, okay, I got pi radians. So if I took the cosine of negative pi, well, that would give me an answer of -1. Well, what happens if I take the cosine of just regular pi? Well, I'd also get -1. These two guys are the same exact answer. And it doesn't matter which angle I pick, it would still be valid. I just happened to grab that one. So what does that mean? It means, well, in the formula here, if I take cosine of a negative angle, whatever it happens to be, it's the same as taking the cosine of the positive angle. So let's suppose I'm working through a problem, and in the question they say cosine of -60 degrees. And I go, you know what? I don't want to use the negative version of that. I think I'll substitute in cosine of regular 60 because they will be equivalent. So some people like to do that. If you know the negative angle identities, you can substitute information and interchange it to make your computations easier. So, what should you remember? You should remember this. That's called the negative angle identities. But I wanted you to see, why do they work? What do they mean? Now the next ones, here we go. We've got reciprocal identities, we've got quotient identities, we've got Pythagorean identities. So guess what? This was Roman numeral 1. I just went through those. Let's talk about the reciprocal identities. Now you might say, wait a minute, cotangent equals 1 over tangent, secant equals 1 over... I already know these ones. We talked about them. Yes, we did. But I need you guys to kind of see into your future here. So it says reciprocal identities. So what you will see is I drew myself a right triangle. And I have a theta. So the thing is, I know that I can do any of these. I could SOHCAHTOA. And what the heck, the first one they have here is tangent. So let's just play with tangent. For any angle theta, see, I drew myself an angle, and it forms a right triangle. I know that the tangent of that would be, well, I could say the tangent of that angle theta would be opposite over adjacent. And why did I use these letters? Well, see this piece of my triangle here? I'm darkening it in right now. That's positive y information. It is. This is positive y information. See this part here, this guy right here? Well, that's positive x information. So I called my variable x and y, and then in our book they use r for like the hypotenuse, the r, and it's just, I got to call them something. So in the book they use x, y, and r. But here we go. The tangent of theta would be y over x. Why? Because of SOHCAHTOA, right? The tangent is the opposite over the adjacent. Okay, I did that. And then we say, well, what would 1 over that look like? What would 1 over that look like? Well, it would look like 1 over y over x. And then I go, wait, that's a double fraction. I don't like double fractions. So I could multiply top and bottom by x. I could. Then this would cancel. And I could say, hey, the result is, when I do 1 over tangent, I get x over y. Well, x over y, like I said, hey, that would be adjacent over opposite. That's cotangent. That's cotangent theta. All of these identities have a reason why they exist. And an identity is basically a fact. It's just a fancy way to say, here is a fact about these things. So, cotangent is the same as 1 over tangent. I could use my triangle here. I could use this drawing and I could show you the same reason why this is true, why this is true. I could do that. What I'm trying to get at is this. If you already have this memorized, you never have to draw yourself a reference triangle. You never have to label it. You never have to go through what I just did to prove that this is true. Try to get these memorized. Okay? You will be happy you did. It will make your life easier. But I want to give you a little glimpse here. You know what? This is not written in the book. But it's a variation on this. See, cotangent is equal to 1 over tangent. That is totally true. But what is also equally true is tangent is equal to 1 over cotangent. It is. See, this guy right here, they don't have it written in the box. You know what? Here, this guy right here, they don't have it written in the box. But this is also true. 1 over secant is equal to cosine. Oh yeah, it goes both ways. It totally does. You know why? Let me show you. I'm going to show you using this one. So we have cosecant theta is equal to 1 over sine theta. So that goes on a flashcard. We go, what is, the reciprocal identity for cosecant? That's a flashcard. But equally valid is this. You could say that sine theta is equal to 1 over cosecant theta. And you might say, well, that's not in the box. Why didn't they put it in the box? The reason they didn't put it in the box is there's so many different variations on this stuff that are true. Take a look at what I have here. I'm going to just show you why this works. If I put a 1 on the bottom here, I didn't change anything. I know it. Also, it looks like a proportion. So if I wanted to, I could cross multiply. And I could say cosecant theta times sine theta equals 1. And then what the heck? I'm going to divide this side by cosecant theta. As long as I divide both sides by the same thing, I'm not changing it. And then look, those would cancel. I get sine theta equals 1 over cosecant theta. Wow. Just let it sink in for a second. Every formula here that I just showed you, there's 1, 2, 3 of them. Well, guess what? There's a very similar situation. So technically, the 3 formulas in that box are now 6 formulas. Could you make flashcards of these also? Yes, you could. But wait, if you act now, you'll also receive the quotient identities. See how quick I did that? If you want, you could pause it, rewind it, go back there. But let's talk about the quotient identities. And these are super powerful. Okay, you ready? Tangent theta equals sine theta divided by cosine theta. It is a fact. Same thing goes here. Cotangent theta is the same as cosine theta divided by sine theta. It is a fact. It is true. It is valid. If I were you, I would memorize it. But if you wanted to, let's just take a little look here and see what's happening. If I wanted to know the sine of theta, right? If I want to know the sine, I would say that's the same thing as opposite over hypotenuse. If I wanted to know what the cosine of theta is, I would say that's adjacent over hypotenuse. And if I wanted to do, and I'm going to come over here, hang on, I'm going to give myself a little room here. If I wanted to do sine theta divided by cosine theta, it would equal, there are so many dogs barking right now in my neighborhood. That's not my dog, by the way. Anyway, so sine theta divided by cosine theta. And I look at that and I say, ooh, what a horrible looking double fraction. I do believe if I multiply the top and bottom by the exact same thing, I'm not changing it, and that would be r, then the r's would cancel here, and I would get y. And the r's would cancel here, and I would get x. Which is the same thing as taking the opposite over the adjacent. That's tangent. Wait a minute. So if I do sine theta divided by cosine theta, what do I get? I get tangent theta. Amazing. It's amazing. Now the same thing, I could do this the other way, and you could see that this is true. It totally is true. So guess what? Would you rather draw a reference triangle? I'm trying to sell this to you. Would you rather draw a reference triangle, find the sine, find the cosine, do the quotient, cancel out your double fractions, see that it's or would you rather just memorize a couple facts? I think I'm making a pretty strong case for memorize a couple facts. But guess what? I just want you to see this too before we go too far. See this guy right here? Hey, I could say this. You know what? I wonder if I squared this side, if it would be the same thing as this side getting squared. Is that true? Yes, that would also be true. So if I wanted to, I could think of it as, just because I know one formula, one little tiny quotient identity, it doesn't mean that's the end of the road. There's all kinds of information. So let's suppose I'm working on a problem, and inside the problem they have cotangent squared theta. And I go, well, wait, what can I do with that? If you wanted to, you could say that's the same as cosine squared theta over sine squared theta. And you might go, whoa, that's a lot of information. I know it. And I haven't even gotten to the last one. So, let's look at it. This guy's the big daddy of them all, Pythagorean identities. Oh, baby. Now, here's the thing with Pythagorean identities. I know, based on my triangle that I have drawn here, we already did this in the last one. I could say the sine of theta, well, that would be opposite over hypotenuse, right? I could say the cosine of theta, that would be the adjacent over the hypotenuse. Totally true. Heck, you know what? Let's soak all the toes here. Let's get them all soaked. That would be opposite over adjacent, right? Well, check this out. Check this out. Pythagorean theorem. Let's just, what? You know what? It's true that x squared plus y squared would equal r squared in this situation. It totally is true. Okay? How do I know that? Because of Pythagoras. So guess what? These guys right here, these three guys right here, lead us to like 12 different variations. We're not going to do every variation here. We're not, because this is the first section. But I do want you to see this. How did I get this statement here? It's just Pythagorean theorem. One leg squared plus the other leg squared equals hypotenuse squared. You with me? Okay, now check this out. As long as I divide everything here by the exact same thing, I'm not really changing it. So guess what I'm about to do? I am about to divide this by r squared. I'm going to divide this by r squared, and I'm going to divide this by r squared. At which case, or which point, you might say, hey, r squared divided by itself is the same thing as 1. And I would say, I am in full agreement. What you might not look at the same way as I do is this. You may not look at this and say, you know what? I bet if I wanted to, I could organize my work like that. Just let that sink in for a second. If x is being squared and r is being squared, I could write it as x divided by r, the whole thing being squared in parentheses. I could equally do that here. And then I look at this and I go, you know what? Dang, x divided by r, that looks really familiar to me. Oh yeah, that's the same as cosine. This y over r, that looks really familiar to me. That's sine. Now, here is something in the book. They mention it, but it's like a little tiny blurb. Just so you know, if I say sine theta times sine theta, I can call that sine theta squared, or I could just say sine squared theta. These are equivalent statements. They are. But it's just, this is kind of like the customary way to do it. You put the squared on the sine part. Don't ask me. That's the way it is. I just follow the rules. But guess what? Cosine squared theta plus sine squared theta equals 1. Well, when you're adding two things together, it doesn't matter which order you put them in, right? Cosine squared theta plus sine, I could write it like this if I wanted. It's still valid. It's the same thing, just rearrange the order, and then you go, dang, that's why that thing is true. That's called the first of our Pythagorean identities. That is called the first of our Pythagorean identities. Guess what? Tangent squared theta plus 1 is equal to secant squared theta. It is totally true. Should you memorize it? I would say it would be a lot easier to memorize some stuff than it is to draw out the pic. I'm trying to keep this in play here. You could do what I just did every single time if you wanted to, or you could just make some flashcards and make your life a little bit easier and memorize some things. Because this one right here, this guy right here, I call it tan in 1 sec. Like if you went to a really, really, really super powered tanning salon and they put you in a super powerful tanning bed, you could get tan in 1 second. Get it? That's how I remember that. Tangent squared theta plus 1 equals secant squared theta, tan in 1 sec. That's how I remember that. Anyway, let's talk about that one, because I'm just going to show you. If I really wanted to, I know this is true. I just showed you this is true. I just proved this thing is true to you. Well, guess what? I am going to choose right now to divide everything here, everything, by the exact same thing. And that exact same thing that I'm going to divide everything by is going to be cosine squared theta. Why not? As long as I divide everybody in the whole shebang by the same thing, and then I go, wait a minute, sine divided by cosine. Wait a minute, that's tangent. And I already talked to you about this. Look at this. What? That's crazy. That's crazy. So this guy right here is like saying tangent squared theta. Plus, well, cosine squared theta divided by itself, that's just 1. And then guess what? 1 over cosine theta, we call that thing secant theta. But if this is squared, that would be squared. And you go, dang, there you go. Tan in 1 sec. Tan in 1 sec. How did I get that? I just took the last fact that I had and I manipulated it. I played around with it a little bit. It's crazy. You do this in trig all the time. In calculus, sometimes we'll have a problem that has more than one function in it, and we go, man, my life would be so much easier if I could convert everything just to one single function. So a lot of the stuff I'm showing you right now, you're going to have to play with this to get good at doing this. But This is the second iteration of this, or variation of this guy. Let's talk about, I'm going to go back. What if I had done this? What if I had chosen to be so bold as to divide everything by sine squared? As long as I divide everybody by the same thing, I'm not really changing it. And then I would get, well, I'd get a 1 plus cosine divided by sine. Wait a minute, we saw that earlier too. That's called cotangent. And if everything's squared, we'll call it cotangent squared. And then this guy, 1 over sine, well, wait a minute, 1 over sine theta, that's equal to cosecant theta. And then I could, oh, if this is squared, that's, oh my gosh. And this is the third of our Pythagorean identities. This is the third one of these. Now, in the book, they don't write 1 plus cotangent squared. They write, look. They do write it that way, 1 plus cotangent squared. Oh, okay. See, I don't write it that way, and I'll tell you why. Because I like some cool tricks to help me remember stuff. So whenever I write this one out, I put this guy first, I put this guy second, and I put this guy last. Because then I think of it as, like when somebody blows a kiss to you, I think of this, caught one kiss. Caught one kiss, kiss, kiss. I'm taking a little bit of liberties there, but that's how I remember this one. That's how I remember it. I think of caught one kiss. And here I think of tan in 1 sec. And here I just think of sine squared theta plus cosine squared theta equals 1. I have nothing really cool for this one. Okay, but guess what? I'm going to scroll up to the top real fast. That is all the stuff on page 191 with a little added something something for you. Remember, I showed you that just because you know this doesn't mean 1 over cotangent equal tangent is invalid. Just because you know this doesn't mean if you throw a squared here, you could do that to both of these. It's true. You could do that. There's one thing that I'm going to tell you, though, that you cannot do. Well, you could do it. It's just totally wrong. It's you do not do something like this. I'm going to take the square root of this. You don't take the root of Pythagorean identities. Okay, I'm going to erase that because I don't want you to think that's true. Okay, you can never, let's say never, dog, you can never take the square root of Pythagorean identities. Don't ever take the square root of these guys. You will not get the right answer, and it's an automatic. Everything else you just did in the problem is wrong. Don't do it. All right, so guys, guess what? Page 191, all that stuff in there, you got to memorize that stuff. You do. Or you could derive it every time and draw reference triangles and build it, but I don't think you want to do that. I really don't think you want to do that. Okay, and I only have one last thing. I'm going to scroll all the way down to show it to you. One last thing. And it has to do with this guy. Well, any of the Pythagorean identities, but I'm going to just pick on this one here. Okay. Okay, so I said make some flashcards. It'll make your life easier. It will, because guess what? Sometimes we don't want to use it looking like this. Sometimes we want to use it looking like this. what did I do? I took the original and I just subtracted cosine squared from both sides. See, sometimes it's more convenient to look at it this way. It's true. Or sometimes it's more convenient to look at it this way. What did I do? I went back to the original and I moved the sine squared to the other side. That's totally valid. Okay, here we go. Ready? Just let that sink in for a second. That is also a way I could rewrite this exact same thing. See this right here? I'm going to get my red pen. Come on, come on, come on, baby. That's the difference of squares. That's the difference of squares. What times itself is 1? 1. What times itself is sine squared? Sine. Oh yeah, this one little chunk leads to all kinds of stuff. And you know what? Let's do it. I could do this version. Oh, sorry, I could do this one right here. I could do this one right here. I could say sine squared theta is equal to 1 plus cosine theta and 1 minus cosine theta, because that's also the difference of two squares. There's 1, 2, 3, 4, 5 different ways I could use the exact same formula. And that's just for sine squared plus cosine squared equals 1. That's just for that one. Guess what? I could do the same thing for tan in 1 sec, and I could do the same thing for cot 1 kisk. So when I started telling you guys to make some flashcards, I was not kidding. I was totally trying to give you guys a solid heads up. Okay, so this first video of Unit 8, this is all you get in this video, is me trying to explain to you there are things out there called fundamental identities, and these fundamental identities have alternative forms sometimes. So see, I left this in here when I took this picture. Like, we also use alternative forms of these. For example, and then see, they did what I did down below, but I even went a little farther than that. Okay, we need these for playing pieces. Over the next couple lessons, we're just going to dink around and play with this stuff. We're going to do identities first, then we're going to do computational trig. So, I hope you get these memorized. I hope you make your flashcards. The next lesson, we're going to start playing with this stuff. Okay, guys. Bye-bye.